Our second speaker is also a first-year Pappalardo Fellow who comes to us from Harvard University with his PhD, Dr. Hugh Churchill. And one interesting fact about Hugh is that in addition to undergraduate degrees in math and physics from Oberlin College, he received a degree in tuba performance from the Oberlin Conservatory of Music. So we're really blessed with the musical talents and interests today, and so glad that you are with us, Jane, to enjoy and share it. Thank you very much. And Hugh will get set up here in a moment, and he will be talking about condensed matter physics, nanoelectronics with atomically layered materials. One of the great things about this program is you get to hear all these amazing descriptions of research from across the field explained by experts who can make it all comprehensible to us. So we are really blessed, and hopefully the technology will allow us to have the nanoelectronics explained by microelectronics. Thank you, Hugh.
Okay, so I'll change the topic from some of the largest length scales in the galaxy to some of the smallest length scales, or the atomic scale. And I'd like to tell you about plans that I have with Pablo Herrero's group to explore some of the physics of nanoscale electronic devices that are built out of materials that are only one or a few atoms thick. And so the most well-known of these materials is graphene, but there's also hexagonal boron nitride, and a newcomer to this area, which is a family of materials represented here by molybdenum disulfide, or MOS2. And I'd like to tell you about some of the properties of these materials, and I'll describe how we make devices using them, devices such as this. And then I'd like to also tell you about some of the experiments that we have planned to investigate the physical properties of those devices that we make. So to provide some context for these plans, I've shown one of the most basic and important electronic devices, which is the transistor. So I have two versions up here. On the left side, you can see a picture of the very first transistor that was made at Bell Labs in 1947 using a high-quality crystal of germanium. That was an object that you could hold in your hand. And then on the right side, I have a picture of the types of transistors that run this laptop computer made by Intel, which a billion or so of which can fit on a small silicon chip. And if you zoom in on that chip using an electron microscope, you can see that apparently modern transistors look sort of like nanoscopic waffle fries. And each individual unit of this waffle fry occupies a space of only tens of nanometers. And so I'd like to make 2 points about these transistors in the context of the work that we have planned in atomically thin materials. And the first of which is that despite the very different sizes and operational principles of these two types of materials, they're both made out of the same basic material components. There's a metal component of both, an insulator component, and also, of course, a semiconductor that makes up these devices. And so these combinations of different material properties are known as heterostructures. And heterostructures are, of course, important technologically for the functionality they provide, but they're also extremely important for basic research in condensed matter physics because they allow us to have a great deal of tunability and control over the physical systems that we're interested in studying. The second point that I'd like to make about these transistors is you can see by comparing the years up here, 2012 and 1947, about 65 years have passed since the invention of the transistor. And so transistors made of traditional semiconductors, such as silicon and germanium, are nearing their retirement age. So in this process of continually scaling them down from sort of hand size down to the nanometer scale, they're getting thinner and thinner and getting whittled down to nothing and approaching an ultimate limit at the atomic scale. So if you zoom in even further on this single functional unit of this modern transistor, you can actually look at the individual silicon atoms that make up the silicon heart of this transistor, and you can count them and see that it's only about 30 atoms wide. So there's a nice situation that arises in condensed matter physics in which these atomically thin materials that I'm interested in studying may naturally occupy a position at sort of the ultimate atomic limit of this scaling down process. And so basic physics questions that are being asked about these atomically thin materials may go hand in hand with the technological development of materials which may be relevant for electronics in the future. So I'd like to now describe a little bit about the properties of these various atomically thin materials I'm interested in studying. The first one to be isolated in a single atomic sheet was, of course, graphene, which is a honeycomb lattice of carbon atoms, which is a semi-metal. Next came hexagonal boron nitride, which is an insulator. And then the newcomer to this area are the semiconductors. There's a whole class of them represented here by molybdenum disulfide. And what unifies all of these materials together is that they can all be purchased in aerosol cans. And the reason for that is that they all make excellent dry lubricants. And they make excellent dry lubricants because all of these materials have intrinsically layered structures. So they're formed out of stacks of two-dimensional crystals, which have very strong chemical bonds within the plane, but have very weak coupling between planes, so that the layers can slide past each other without breaking, which provides lubrication. And that same sliding for lubrication is what allows us to peel the layers apart and isolate individual atomic layers for study and making devices to look at the physics of these materials. So I'd like to say a little bit about the properties of these various things. Graphene, the semi-metal, has probably the most unique properties of these three. It has an energy-momentum relationship which is linear, that makes the electrons in this material behave as if they're massless. Hexagonal boron nitride has a structure that's identical to graphene's, except that each of the carbon atoms are replaced by alternating atoms of boron and nitrogen. And that gives it a very large band gap, so it's an excellent insulator. The band gap is just the separation in energy between the electrons in the conduction band and the holes in the valence band. And it's kind of the first thing you want to know about some semiconductor or insulator to characterize its properties. And then the newest addition to the toolbox of these atomically thin materials is this class of materials represented by molybdenum disulfide, and its structure is a little bit different. It's actually composed of stacks of atomic trilayers. So there's a layer of molybdenum atoms in the center that's sandwiched between two layers of sulfur atoms. And its band gap is intermediate between boron nitride and graphene. It's a semiconductor. And in addition, unlike graphene, it has another property, which is a strong spin-orbit coupling, which just means that the energies of the holes in this valence band depend on the direction of the spins of those holes. So now that we have these three materials with the properties required for making sort of generic heterostructures for electronic devices, our vision is to stack them up and make heterostructures all based on these atomically layered materials. And I should say that later in this symposium, Andrea will talk about a heterostructure of these first two, in which the combination of graphene and boron nitride fundamentally alters the properties of the graphene. And so now I'd like to talk a little bit about how we fabricate devices using these materials. So the starting point is this Scotch tape exfoliation technique that was made famous by graphene, in which single layers of graphene can be deposited on a silicon target chip. And then using the same trick, a second layer that's going to form the second layer of this heterostructure is applied also by Scotch tape onto a transfer stamp that's composed of a piece of silicone and a polymer that, when it's heated up, will release from the silicone. So what's done is we apply the layered material on top of the stamp, turn it over, align it with the target chip, press it down, heat it up, and when the stamp is lifted off, the heterostructure forms on that target chip as desired. So I labeled this slide stacking atomic layers by hand, and to show that that's in fact what we do, I have a picture of the setup that we use, and here's my index finger near the microscope, the target chip, and the transfer stamp that we use. And here are some optical microscope images of one such device made by Britt Bogger, who's a graduate student in the Rio Herrero lab. So it starts out with deposition of graphite on a silicon chip, then hexagonal boron nitride is added, then a layer of molybdenum disulfide, and finally gold contacts are applied to the molybdenum disulfide so we can do electrical measurements on that semiconductor in this heterostructure. So now I'd like to say a little bit more about the properties of this newest addition to these layered materials, which have probably one of the most difficult to pronounce names in all of physics. They're the transition metal dichalcogenides. And they're formed by selecting a transition metal from the center of the periodic table and picking 2 atoms from the chalcogen column of the periodic table. The chalcogen means ore forming, and the reason for that is that whenever you want to dig up metals out of the ground, they typically don't come out as pure metals, but instead as compounds, most frequently oxides or sulfides. So that's why the chalcogens are so named. And as one example, here's a picture of one of the largest molybdenum mines in the world in Idaho. And when molybdenum is extracted from this mine for use in steel, for example, it doesn't come out as pure molybdenum, but instead comes out as molybdenite, which is in fact MOS2. And because these crystals can be quite large and shiny, people sell them on eBay. So depending on which elements are selected to make these dichalcogenides, the properties can vary widely from large gap semiconductors to small gap semiconductors or metals, which ultimately become superconducting at low temperatures. For our purposes, we're interested in adding a semiconductor component to these heterostructures, so we'll focus on compounds of molybdenum and tungsten, sulfur and selenium, which all have a large semiconducting band gap that we can use for that purpose. And in general, for these layered materials, when they're thinned down to only a few atomic layers, they become flexible and transparent, which may have interesting technological applications. And in addition, the physical properties of these materials depend very sensitively on how many layers there are. So for example, a single layer of molybdenum disulfide has a 50% larger band gap than a bilayer of molybdenum disulfide. So we've done some initial measurements on these materials. So here's a bilayer of molybdenum disulfide that we've contacted with gold, and we can measure then current flowing through the molybdenum disulfide as a function of voltage that we apply to the silicon substrate that this thing is sitting on. And for example, consistent with other groups around the world who are working on these things, we see that this material does in fact behave like a transistor. A transistor is just an electrical on-off switch. When it's on, there's a large current passing through the device, and when it's turned off, the current has been reduced to just a trickle. In addition, when we want to investigate sort of the intrinsic physical properties of these materials, we'd like for the electrons to travel a long way through the material before they hit some impurity and change their direction. And this length that they can travel before that happens is quantified by the mobility, which we found in these devices to increase substantially as the temperature was reduced. So I should say that while these values are sort of state-of-the-art for these materials, they're not as high as we'd like, and so improving this number will be a focus of future work for these materials. So now I'd like to describe some of the experiments that we want to do going forward to investigate some of the sort of unique properties of the dichalcogenides. And the first one is to investigate a feature of the electronic structure of these materials known as the valley, which just reflects the orbital momentum of an electron as it moves from atom to atom through the crystal. So the hexagonal lattice that describes these materials when viewed from the top actually has to be decomposed as 2 sublattices, A and B, that I've colored red and green here. And those 2 sublattices imply that there should be 2 valleys with differing momenta that are important in the electronic structure of this material. And to understand why these things are called valleys, it's useful to look at the energy-momentum relation. You see that there are 2 minima in the energy that we see. So these minima are the valleys. That's the origin of the term. And so there are particular places where these minima are just labeled K and K prime. And both the dichalcogenides, such as MOS2 and graphene, they both possess this valley structure in their electronic structure. So one thing we're interested in is whether we can do valley-based electronics or valleytronics. And the question is whether these different valleys, K and K prime, can actually be controlled and manipulated and used for computing. And early on in the days of graphene, it was thought that perhaps graphene would be a good candidate for this pursuit. But in graphene, the A and B atoms are identical. They're both carbon. And this symmetrical property of graphene is largely responsible for many of its unique electrical properties, but it means that it's difficult to distinguish the valleys from each other. But in the dichalcogenides, the A and B atoms are different. The A atoms are molybdenum and the B atoms are sulfur, for example. And then there's some hope that the valleys could be distinguished in these materials. So a first step in that direction would be to observe a valley-based analog of the Hall effect that's been known for a long time. And in fact, condensed matter physicists are frequently criticized for only ever measuring resistance as a function of magnetic field. And a big reason for that is our love of the Hall effect. And the idea is just that when a current flows through a device in the presence of a perpendicular magnetic field, the electrons are deflected to one side of the sample, resulting in a voltage that can be measured. And it's one of the most important tools for characterizing semiconductors because, for example, depending on the sign of this voltage that you measure, you can find out whether the carriers in the material have positive or negative charge. About 10 years ago, it was found that there's an analog to the Hall effect for charges involving the spin of the electrons. And in materials which have a strong spin-orbit coupling, which simply means that the direction of the spin of the electron is tied to its motion through the crystal, in these strong spin-orbit coupling materials, spin-up electrons can veer up in the sample and spin-down electrons can veer down. And so this segregation of spins on opposite sides of the sample was observed about 10 years ago. So by analogy to that, it was proposed very recently that there could be a valley-based Hall effect, the Valley Hall effect. And the idea is simply that, sort of similar to the spin Hall effect, because of the different momenta of those two valleys, electrons in the K valley, for example, will drift to the top of the sample, and electrons in the K prime valley will drift to the bottom of the sample. And so there will be populations of just one valley on either side. But because there's no charge associated with these, there's no difference in charge between these two valleys, so there's no voltage to measure. So one question is, what do you measure in this case? And I should point out that the situation is reversed for holes. So whereas electrons from the K valley go up, holes from the K prime valley go up. So that means that if you have a situation with both electrons and holes in the system, it would spoil this valley effect, as you would get, for example, if you excite electron-hole pairs in the material with a laser. But it was found last year by several groups that you could selectively excite electron-hole pairs from just one valley by using circularly polarized light. So the idea is that if you use, for example, clockwise polarized light, only K electrons and K holes get excited, and the K electrons will go to the top of the sample, and the K holes will go to the bottom of the sample. And so then you would have some valley-dependent voltage that you could measure in this case. And as a check that is in fact what's going on in the system, you could switch from clockwise to counterclockwise light, and then the sign of this Valley Hall voltage ought to reverse. So I'd like to briefly just describe two other experiments that we have in mind for investigating the properties of these dichalcogenides. One is that the band gap of a bilayer of molybdenum disulfide ought to shrink dramatically in an electric field. So if we make a stack of these atomically layered materials into a heterostructure like this and apply an electric field transverse to this bilayer of molybdenum disulfide in the middle, with an electric field sort of as large as we can make before the device breaks down, we ought to be able to substantially reduce the size of this band gap, for example, by half an electron volt or so. Finally, another topic that we're interested in looking at is investigating some of the quite surprising superconducting properties of these materials that were discovered by Yoshihiro Iwasa's group last year. So when I showed you the transistor data before, where we were able to change it from a metallic conductor in the on state to an insulator in the off state by changing a gate voltage, here, by going to even higher gate voltages and higher electron densities, they're able to go from insulator to metal all the way to a superconducting state when the temperature was cooled below 10 Kelvin, which means that you can access this entire range of properties of the material simply by changing a gate voltage. And what that means is it's then possible to imagine patterning where on a sample these various properties exist, for example, by having several independently controllable voltages in different places on the sample. So for example, you could make a superconducting, normal superconducting Josephson junction device that would all be made out of the same material, which would be quite interesting. So I'd like to summarize sort of with an outlook for our plans in this area, given that we have metallic, semiconducting, and insulating materials all in these atomically thin materials, we can create heterostructures for new experiments in nanoelectronics. And we look forward to investigating things such as the Valley Hall effect and this tunable band gap and gate-defined superconductivity in these materials. And I want to say that MIT has become a great place to carry out this work because of a large and growing community of people interested in layered materials, including dichalcogenides, from large-scale growth of the materials to integrated digital circuits to photovoltaics and ultrafast spectroscopy. And finally, I'd just like to acknowledge Pablo Herrero and his graduate students, Britt Bogger and Yafang Yang, who are working with me on these materials. And also, of course, most of all, Jane and Neil Pappalardo for making it possible for me to do these experiments at MIT. Thank you.
Wow. Thank you, Hugh.
Did you, when you, in the earlier slide, when you were indicating it could act like a switch, granted it's a large device and therefore the time it takes to switch from one state to the other. Did you do any measurements of that, or at least extrapolate it if you can make it smaller and smaller? What's the limiting factor of time it takes to switch?
So we haven't done ourselves measurements of this time scale, but one reason that people are interested in these atomically thin materials is that they should be able to operate much faster, because the limitation in that case is the capacitance that's set by the size. And so if you make it really thin, you can potentially go much faster, but it hasn't been demonstrated as far as I know.
Wolfgang.
So you talked about two new graphene-like materials. My question is, to what extent have people now looked through all possible materials and figured out if they can get atomically thin layers? Are those now the kind of materials we have at our disposal, or do you expect many more discoveries of such layered materials?
So I think of the ones that are sort of available naturally, it's likely that these are sort of the ones that are around. You know, I thought, well, maybe all these things are dry lubricants. Maybe that I can just look at dry lubricant catalogs and figure out what material to use. But if you look on Wikipedia, it has graphite and boron nitride and molybdenum disulfide. So at least the common ones. But I would be very surprised if there weren't new ones that are discovered. This isn't a complete list. There are a few others. There's some layered superconductors, for example, and other things. But I certainly expect that more will be discovered.
I think I'm going to go check my deodorant. Other questions? Yes.
What is the global distribution of molybdenum? And slightly not so serious, so do you stop your lab from eBay?
In fact, we do have a piece, to answer the second question, we do have a piece of molybdenite that we got from another group where somebody was selling kilograms of molybdenum disulfide on eBay, and they snatched it up and broke off a piece and sent it to us. We haven't done any measurements on it yet, but they claim that it's pretty good. As far as the global distribution, I'm not totally sure. I know that there are a lot of mines in the Rockies and in Australia, for example. So it's generally around, but not so abundant in the Earth's crust.
I think it is one of the critical elements that is maybe hard to get and is certainly produced in large amounts in China. And I gather it's an economic question as to when it becomes economically attractive to open up the mines in the Rockies. Molybdenum, I remember that as one. Are there other questions on the subject? I wanted to ask, I guess, following up that waffle iron question, I can imagine that making such a nanoscopic device is extremely difficult and would require very specialized facilities. On the other hand, you showed something that was macroscopic that you could put together by hand. What's your vision of where will you go with this? What kind of facilities are needed for this sort of work? What can be done at MIT, and what are we lacking here? I'll ask a department head type question.
Sure. So I think what's difficult about the transistors that appear in laptops is that they have to make of order 1 billion of them, and they should, a large fraction of them ought to work. for our purposes, the vertical dimension of these layered materials is 1 or 3 atoms thick, but the lateral size at this stage is microns, or some fraction of a micron or so. And so using standard electron beam lithography techniques that are available at MIT, we're able to make the sorts of devices that we want. So we're not limited by the resolution of the tools that are available.
Okay, and then somebody has to attach those gold leads. Is that what the microscope is for? Finding out where to attach the gold leads?
So what you want to do is look around on the chip and find out where you have these single atomic layers, and then you take a picture of it and then load it into a CAD program and then design it. And these lithography tools that I described are what actually write the patterns for the electrodes in the device.
Great. Max?
Since you were joking about 65 is kind of retirement age for today's foundations of today's computer technology, and since Frank Wilczek, I don't see him around here today, but I'll ask a question which he often asks. He likes to talk about today's computer chips as basically moving electrons around in 2 dimensions. You are pioneering going to this very small scales and have undoubtedly thought more wide-ranging thoughts about where this is all going than many others. So do you want to speculate a bit about building truly 3D chips down during the next 65 years? What do you think might be possible?
I don't know. I mean, certainly, they can be stacked. So an advantage of these materials is that because they have weak interactions between those layers, it's possible to stack up very different materials on top of each other. So it's certainly conceivable that some extra dimension of structure could be added. Of course, you have to worry about connecting all the different layers and things like that, which is a big challenge. So I guess to say it briefly, I haven't thought a lot about that aspect of this scaling problem.
But he is adding spin. He is adding a new element, and that's very valuable. Hugh, thank you for a very illuminating talk.